Okay, let's get started. We are entering the last 3 weeks of our class. We have finished talking about the memory safety and memory security issues. We didn't really cover everything. There are other things like free use after free vulnerabilities, those kind of things. I didn't cover in the class because I really want to talk about a very pressing issue, which is cache side channel attack and also other attacks related to it, like the very infamous meltdown and spectral attacks. Those are very hot topic in the last 15 years. Like the beginning, it was like a toy. People do not know how this can do real world damages. Then combined with other techniques, people find out meltdown and spectral in the last 2-3 years, which uh, basically discovered some vulnerability in all our CPUs for decades. So today we will start talking about cache side channel attack. Then obviously before that we'll talk about what is cache, how cache works. So in the last 40 years or even longer, the speed gap between your CPU and the main memory. So the main memory, usually we're talking about the DRAM, is getting bigger and bigger. CPU is getting faster and faster. DRAM is also getting faster and faster, but the speed DRAM is getting faster is nowhere near our CPUs. So the perfect memory or storage system should be super fast, like as fast as the computing modules, as fast as the CPU, and super large, super affordable. Unfortunately, that doesn't really happen in reality. We don't have such memory storage systems. If we have something it's super fast, super large, super cheap, then we do not need different layers of storage. So right now, our solution is to have different layers of storage. The faster ones are usually more expensive and also smaller. And there are more affordable ones, larger ones, but they are quite slow. So the speed, the cost, the capacity, and also there are other factors, benefits. They are more like trade-offs. You cannot get all of them on one device. And the strategy to handle the speed gap between CPU and storage is to put the faster memories closer to CPU and keep frequently use the code data in the faster storage. So we don't have to resort to slow storage very often. We don't have to resort to slow storage every time. And this is a multi-layered solution. And at the layer that is closest to the CPU is the CPU cache. So CPU cache is something between your computing module of the CPU, like registers, computing modules, and also the main memory. So CPU cache is so when I talk about cache in this class, we are specifically talking about CPU cache. We're not talking about other concepts of cache. For example, if you visit a website, your browser will caching things locally in a file. Those are not the things we're talking about. We're talking about a physical device called CPU cache. And that physical device is part of the CPU die itself. It's on chip. It's very small compared to your main storage. It's very small. It's very expensive. It's as expensive as the CPU itself because it's usually made by SRAM. So SRAM is much faster than DRAM because you don't need to recharge it. So DRAM, dynamic RAM, usually you have you need to use what? You need to use a capacitor. What's that called? At a circuit level, you need to use a capacitor. What capacitor? I think. And the resistance and also some gates. Yeah. Oh no, just the resistor and the capacitor. But the capacitor will leak electricity, right? So you have to recharge it. And the SRAM is made by 6 gates. So it's much more expensive, but it's very, very fast, and you don't have to recharge it. So to make the CPU, to make your computer run faster, we keep a copy of the most frequently used data in the cache. So when the CPU wants to use that data, it goes to the cache instead of going to the main memory. Okay. And the cache are also divided into multiple layers. And all the layers of the CPU cache, they are integrated onto the processor itself. So here is a table showing some data of accessing time from the CPU, from the, if you want to load something from somewhere to register, how long does it take? If you are just loading something from cache, it will take half or 2.5 nanoseconds. If you want to move some data from memory to register, so this is an instruction we have been saying a lot, like a move EAX to a memory location. So if that really is moving data from memory location to the register, it takes 50 to 70 nanoseconds. However, usually cache is transparent to software developers. The software developers from the instruction set level, the instructions only move data from memory to register. There is no instruction to move data from cache to register. That's transparent for software developers or system developers. But under the hood, the CPU will decide if I'm actually moving things from the memory or from the cache to the register. Then there are other secondary storages like a flash or magnetic disks, and then they are much, much slower. However, they are very cheap, and some of them are even persistent, right? Static RAM, dynamic RAM, they're not persistent anyway. If there is no electricity, you don't get the data. Of course, there is another tricky thing is, for example, you have a DRAM, then your computer, your DRAM lost power, lost electricity. The data in that DRAM doesn't disappear right away. It will fade away in minutes. So you can imagine there are a lot of attacks, cold boot attack, hot boot attack, try to retrieve data from the DRAM after reboot or something like that. So there are two important concepts related to cache. One is called cache hit, another is called cache miss. So a cache hit means that the cache contains the data we are looking for. The cache contains the data the CPU is looking for, so the CPU doesn't have to ask data from the main memory. The cache has it. That's called a cache hit. A cache miss is the opposite, which means the data the CPU wants is not really in the cache, so the CPU has to go to the main memory to request for the data. Again, this is only happened under the hood, under the instruction set architecture layer. And instruction layer, it's the same instruction. The instruction is just to move from memory to register. However, under the hood, the CPU will decide if it is in the cache or it's not in the cache. Okay. Then the cache, well, this is something you probably hear. I mean, now when you purchase a computer, you purchase a laptop or a phone, when they list their CPUs, you probably take a look at how many, the cache size of that CPU. So that's exactly what we're talking about here. The cache is divided into multiple layers, and level 1 cache is closest to the computing unit, and most architectures L1 cache is divided into code and data cache. So we talked about this. This is called the Harvard architecture. However, L3 or L2 cache, obviously they are further away from the CPU. When I say further away, I mean physically they are further away from the CPU. I will show you several pictures later. You can see that physically they are, even though the CPU is very small, but physically there is a distance, and that will corresponds to probably 1 nanosecond or 2 nanosecond difference, the distance between them. And also for L2 and L3 cache, usually they are unified, which means code and data, they are stored together. Uh, we don't separate. We don't have a separate L2 cache for uh, code and data. And also, usually L1 cache is only specific to one CPU core. Modern CPUs, they have multiple cores. The L1 cache is specific to each core. They don't share that. L2 cache probably shared by multiple cores, but not all the cores. And L3 cache is much bigger and shared by all the cores. So this is a picture of a very old CPU. I'm not really sure what this CPU is, but we can say that this is probably a RISC architecture CPU. We have a load store component. We have an execution unit. And if you look at this CPU, the size is not very big, but the biggest area is cache. Okay, so half of this area is a L2 cache. This is 1 megabit. So this is a very old CPU. This is half of the CPU. It's 1 megabyte L2 cache. Then we can also find L1 cache. So this is L1 cache. One is the data cache. Another one is the instruction cache. So you can see at least 60 or 70% of this die area is used for cache. So you can see this is very, very important component in a CPU. Here is another old CPU, Pentium 4. So this was brought to market like 17 years ago. As you can see, this CPU, let's see if we can find cache. So we can find it here. We have L2 cache. There are two different L2 cache. This part is actually also cache, but this is a special cache. This is called a TLB, translation look aside buffer. So this cache is specifically used by the memory management unit so the memory management unit will translate virtual address to physical address. And that could be a very slow procedure because when you translate a virtual address to a physical address, you learn this from your operating system class. You need to look up a table in the main memory. And that memory table has multiple layers. There is like a page table, directory, page table entries. This has multiple layers. For Linux, it's usually 3 or 4 layers. So which means if you want to translate a memory address, just the address, virtual address to physical address, you probably need to read the physical memory, the main memory, the DRAM, multiple times. And look up that table for multiple times. It's very slow. So to speed this up, whenever you translate an address, you would place it into some kind of a cache. So next time you need to do that, you don't need to translate it again. You just go to that cache to look up. And this cache, TRB, is translation look aside buffer, is specifically for that purpose. So when you take the operating system class, when you learn MMU, when they talk about the TRB, you can imagine that most cases now, especially now, we are talking about the cache is a hardware device inside your CPU. It's not some cache in your memory. Okay. I don't know if we can find other cache here. I do not really see where is L1 cache. I do not really see it here. So this is L2 cache. I have another picture here. This is a much newer CPU. I don't really know which CPU this is. I downloaded online a long time ago from somewhere. You can see that there are 8 CPU cores there. This is probably a desktop or server level CPU. We have the memory controller part, including the memory management unit. So we have other AI parts for the CPU to connect it to peripherals. We have 8 cores here, and you can see this part. Uh, Probably this is like 20% of the size of the die. So this part is a shared L3 cache. So all the cores, all the 8 cores are connected to this shared L3 cache. So this is called the L3. Also, this is called the last level cache. Um, for ARM CPUs, usually we don't have for the phones you are using, the tablets you are using, most of them use ARM CPUs. That's also where I do my research on. So ARM CPUs usually you don't have 3 levels of cache, just 2 levels. So you don't have this part. So the last level cache for ARM CPU is L2 in most cases. So this is L3 cache connected to all the cores. And you can also see inside each core, this part looks similar like this part, right? So this part is probably the cache. This could be the L1 and maybe even L2 cache. I'm not sure if this CPU, the cores, they share L2 cache. So this part looks like cache as well. So each core has their own cache. Um, Even though, for example, this core doesn't directly use the cache of the core next to it, there could be circuit between them to make things a little bit faster. That happens as well. There are protocols to do that. And one of the scenarios for this is, so imagine you are doing cloud computing. When you do cloud computing, you have many powerful machines, powerful physical boxes. On top of that, you run your virtual machines. And let's say we have a powerful machine with 8 cores. And on top of that, you run 2 virtual machines, and each of them use 4 CPU cores. Then it could be divided like this. Those 4 cores belongs to virtual machine 1, and those 4 cores belongs to virtual machine 2. So even though at the very high level, those 2 virtual machines, technically they don't know they are residing on one physical machine with each other. They don't, right? But they are. They are actually sharing something. They are sharing the L3 cache. So they can communicate with each other through other interfaces. For example, a socket from network. One virtual machine can run an HTTP server, and the other one can use a browser to visit that HTTP servers through the network. That is the channel we want them to communicate with. But actually, they can also communicate with this shared cache some way, somehow. Okay, it's not very straightforward, but they can. That's what we're going to talk about there. And also because they physically share cache, share the CPU, one virtual machine can be used to attack or steal things on the other physical machine. Imagine one virtual machine is running some crypto algorithms. When you run crypto algorithms, something is sensitive data is brought into the CPU cache, right? There are move instructions to move data from memory to registers. A byproduct of that is the data will be moved into cache. So the data will be moved into the L3 cache and the L1, L2. Then the other machine can use all kinds of tricks to infer what is in those L3 cache, hence attack the virtual machine, the other virtual machine. Of course, modern CPUs At least I haven't seen any CPU that directly offer you interfaces for you to read cache. For example, there is no instruction saying move cache to register. There is no instruction to do that. If there is an instruction to do that, it means you can get the value in the cache. There is no instruction to do that, or instruction to dump what is the cache to any kind of port or JTAG or whatever. Usually, I have seen some CPUs claim that they have a cache debugging feature that you can do that, but it's only in document. I haven't seen any CPU can do that. Okay. Another very, very important concept. There are so many concepts associated with cache. We're trying to go over all of them today, so it will be easier for you to understand how all the attacks works later. Obviously, for efficient reasons, when you move things from memory to register, when you move things from memory to register through the cache, you do not move things just byte by byte. It will be very inefficient. Instead, you always move a very small unit of data, and that's a minimum unit of data you want to move from memory to cache. And for modern CPUs, Intel and ARM, that is called the size of a cache line or cache block. That's a minimum unit of information that can be either presented or not presented in a cache. And that is 64 bytes for modern Intel CPUs and ARM CPUs. So there are 64 bytes of it, which means you need 6 bits, right? 2 to the power of 6. 2 to the power of 6 is 64, to the power of 4 is 5 is 32, right? So which means you need 60 bits to represent each byte of that data, the address of each bit of that data, right? 6 bits. Remember that. We're going to use that later. Okay. There is another concept called N-way set associative cache. This is not easy to remember. I will share some animation later. What is the easy way to put it? So this is like years, decades of design in cache, and we right now we end up here. We can't, most of the caches we're using today, no matter what CPU you are using, they are N-way set associative cache, which means any given block or line, which is 64 bytes, in the main memory, when it is placed in the cache, there are many different locations in the cache you can use to place it. And there are N locations for it. Of course, those locations, they are somehow, they share some kind of characteristics, okay? And those N cache lines, you can place a given block or line, that's called a cache set. So for any 64 bytes. No, I should not say any 64 bytes because those 64 bytes may in 2 different cache lines, right? Let's say any given block or line in the memory, there is only one cache set. The content it can go to when it is placed in the cache. However, in that cache set, there are N different cache lines. I will show you some animations, and it will be easier for you to understand. Here we have a imaginary CPU. This CPU has a cache. It doesn't really matter which layer it is. Let's say this is a level 1 cache. This level 1 cache, let's assume we're talking about 1 core, just the 1 CPU, 1 core, doesn't care about what is this virtual address or physical address. Let's assume everything is physical address. Everything is physical address. There is 32 kilobytes of cache. and each cache line is still 64 bytes. Then this is a 32-bit computer, which means the address is the address space is 62-bit, and also probably when you compute on data, most data are also 32 bits, 4 bytes. So this could be some low-end RISC architecture CPU, and this is the address. Okay, so for any memory location, it has an address like this. It has 32 bits. The last, we can call the last 6 bits the offset. What is the offset? This is an offset inside a cache line, right? Why 6 bits? Because we have 64 bytes per line or per block. So we need 6 bits to represent each byte. Then bit 6 to bit 12 are used as the index. It's called the index or set number. And the bit 17 to 31, they are called the temp. So for this CPU, for this cache, so how many sets do we have? First of all, the total cache size is 32 kilobyte, right? So it's 32 times 1024. Then how many ways we have? This is a 4-way cache. It's listed here. This is a 4-way cache. Then each cache line is 64 bytes, which means, so if we divided this, use cache, the number of sets is the cache line divided by number of ways and times the line size. So we get, there are 128 cache sets for this cache. So 128 means, so you need 7 bits to represent that, which means the offset is 6 bits. The set or index part is 7 bits. 7 bits is 128. And everything higher than that, we just call it a temp. Okay. So let's say we have our address. We have an address in the memory. That address can be used to represent a block or line, which is 64 bytes. And we want to move that. We want to move any of those, let's say we want to move 4 bytes in that, any of those 4 bytes in that 64 bytes into the register from memory. Then what happened under the hood is the whole 64 bytes, not only the 4 bytes you want to move. Okay, you have seen instructions like move memory location to EAX. That instruction, from the system developer or software developer's perspective, is only moving 4 bytes. But under the hood, it's moving at least 64 bytes or even more. Because those 4 bytes could be, across the boundary. That's why you see a lot of instructions, they require those memory addresses to align to some boundary. It will make sense faster. Sometimes also at the circuit level, they have to do it. Okay. So even if you're moving 4 bytes from a memory to the register, the CPU actually moves the 64 bytes that 4 bytes belongs to the cache first. Well, there's another thing is at system level, you can say if this memory is cacheable. If it's cacheable, they will move that to cache first. There are things you should never cache. For example, if the peripheral is memory mapped, every time you read the peripheral, it will be different. It's not like the main memory. If you don't change it, if there is no DMA, it will never change. But peripheral, it could be a sensor. So every time you read it, it's different. So you're not supposed to cache it. If you cache it, you're getting obsolete down, right? So you're not supposed to cache it. So then we're moving all 64 bytes into the CPU cache. And for this CPU, because this is a four-way CPU, and which means there are four different locations we can put that 64 bytes. We can put it in way 0, way 1, way 2, or way 3, okay? But we cannot put it in a different set. So each column here I draw here is called a way. And each row I draw here is called a set. As you can see that we already calculated for this one, it's supposed to be 128 sets, which is represented by these 7 bits in its address. Okay, so you can see that for any of those bytes in that 64 bytes, this part will be the same. Okay, the only difference will be the offset. As long as these 7 bits are the same, they belong to the same set, and the set is also labeled as from 0 to 127. Okay, but which way they will get into? That's a different question. That's a different thing. You know, it doesn't really matter. It's usually random. Depends on which way is available. Okay, but you can see that what is actually stored in the cache? Obviously, you have to store the data. And the data is 64 bytes, right? Obviously, you have to store the data into the cache. Besides the data, let's say if we can reconstruct the address, let's say there is something in the cache. How can we reconstruct its address? We don't need to reconstruct the offset part because we put all 64 bytes in here. We don't need to construct this 7 bytes because it will be the same as its index in the cache. If the data is put here, then we know the middle 7 bits will be 127. Okay, but this part, this is like 19 bytes. This 19 bytes, we cannot reconstruct from here. That's why this 19 bytes we also need to store in the cache. So each cache line, we're actually storing 64 bytes of data. We're storing the tag, and also there are some other metadata. For example, if this entry is valid, if this entry is dirty. Dirty means the CPU already changed this entry, but we haven't written this back to the main memory. It happens a lot. Imagine you are designing a cache. You already bring something into the cache, then your CPU will continuously change this cache, do operations on this data. So what you can do is every time the CPU changes the data, you write it back to the main CPU. But writing to the main memory. But writing to the main memory is also slow, right? If you are doing 10 calculations in 100 milliseconds, then why do you want to write things back to the main CPU, which each write may take much longer, 200 milliseconds, right? Instead, you probably will just do the calculation on the CPU, on the cache, and only write it back to the memory when you have to. So you need at least 1 bit to indicate if the CPU has changed the value of the cache. If the data in the cache and the data in the main memory, they are consistent. And that is the dirty bit. Also, there is a valid bit to indicate whether we're actually storing data here or it's just garbage right now. So that is n-way set associated cache. So several terms you need to remember. One is way, another is set. So usually I draw way in each column and I draw ways in each row. And the cache time for the CPUs we are using, they are always 64 bytes. Another concept is congruent addresses. Obviously, the cache is a much smaller device than the main memory. The main memory right now you are using probably is 16 gigabytes or even bigger, even 32. So the CPU, the laptop I'm using right now is I have 32 gigabytes of memory. But the cache compared to that, the cache is very small. So let's say this is my local computer. I just do a LS CPU. You can say this is a quite powerful CPU. Um, we have 8 CPUs, 8 cores. We have 8 cores, and it's like a 3 gigahertz and the virtualization technologies. But you can see this is a cache part. Even though my main memory is 32 gigabyte, this is a very powerful CPU. The cache is very small compared to the main memory. The L3 cache, which is the biggest, is 8 megabytes. L2 cache is only 2 megabytes, and the L1 cache, we have the data cache. D is data cache, I is instruction cache. The instruction cache is only 128 kilobyte. The data cache is only 182 kilobytes. So that's it. But compared to the main CPU, the main memory, it's still very small. And also, remember, the L1 cache is divided by each CPU core. So I have actually another virtual machine running here. Let me show you the virtual machine. So for this class, we're going to do the test in this virtual machine. There is a professor from Syracuse. He developed the SIGNAP. So my name is for this class are based on the SIGNAP. I will make some changes, especially what you do next week. Will be make some changes, but it's based on this. As you can see, so this virtual machine I only assigned it with 2 CPUs. They are physical CPUs on my computer. So if I do a LS CPU on this machine, you can see this virtual machine is only 32-bit. So here we're saying it's a 32-bit, and the physical core is actually can do 32 or 64-bit. It has only 2 cores, and the cache is only 20. The instruction cache is only 32K. Here the L2 the instruction cache is 128 because this is 8 cores. This is only 2 cores, right? And L3 cache is the same. L2 cache the same? No, yeah. So which means L2 cache is not shared by all the CPUs. So L2 cache is probably only it's not shared. It's probably not shared. Yeah. So only L3 is shared. You can see here. And this is so basically this is L1 cache for those 2 cores. So you're supposed to divide it by 2 because each core has half of this. Any questions so far?
I got one, Dr. Zhao.
Yeah.
Is your machine multi-threaded to 8, or is it actually and is a quad core, or does it have 8 physical?
I think it's a 8 physical.
Okay, because I've got an i5 10th gen, and it's showing 8 when I run it too, and I'm pretty sure the i5s are never 8 cores, if I remember right, but I might have that wrong.
Yes. Yeah. Okay, then. So because the cache is much smaller than the main memory, which means there is no way for you to put all the data from the main memory to the cache, right? You can only put certain data from the main memory to the cache. If the cache is full, you want to put new data there, then you have to move some data out. Then there is some replacement policy to do that. Before we talk about that, then we will talk about what is congruent addresses. Basically, based on our calculation here, this figure, you know that many different addresses. Uh, Basically, what should I say? Um, as long as for those addresses, their set part, those 7 bits, they are the same. Then they are supposed to go to the same cache set, no matter which cache way. They're supposed to go to the same cache set, right? Which means they have to compete with each other. And those addresses are called the congruent addresses. So basically, they are addresses that map to the same cache set. Okay. Uh, we don't really care about the cache line part. For example, this cache set has 4 different cache lines. So each of those smallest box, we can call it a cache line. And each column is a cache way, each row is a cache set, each smaller box is a cache line. We don't really, uh, first of all, we cannot specify which cache line it goes to. We cannot specify which cache way it goes to. We can only know which cache set it goes to because they share. And if you bring the same data, the data at the same address to the register twice, and in the middle you flush it from the cache. In the middle, you guarantee it's not in the cache. So the first time you bring it to the cache, the second time you bring it to cache, they may be at different cache lines. The first time it could be here, the second time it could be here. Okay, but it's guaranteed that it's always the same set. Because of the cache is much smaller, you need different policies when you replace existing cache with existing data with new data, right? So this is those algorithms are similar to the one you started in let's say OS scheduler class, right? The scheduler, there may be also algorithms to try to make things fair. And for example, we can do a least recently used algorithm. Which cache line is least recently used? That no one has been using the data in that cache line for a while. Then the CPU can evict that cache line to make new room for new data. But you can imagine, in order to implement this, you need some kind of circuit. Everything here we're talking about circuit. It's not software. You need to least recently used. What do you need to record there? At least you need to, let's say, how many bits you need. For example, here we have 4. Here we have 4 cache lines. We want to remember which one is least used. It's not like we can just do this with 2 bits. We need multiple bits to do that. One way to do it is each cache line, we have several bits to say when this one was last used. That will use a lot of circuit. Or you have a rack of those 4, yeah, it will be the same thing actually. So you can imagine you need multiple bits to do that, and also you need a circuits to compare that which one was least used. So even though this approach sounds like a very good approach at a very high level, to implement it, it could be very expensive. Then there could be first in, first out approach, not necessarily a really good approach, or at least a frequently used approach that you also need multiple bits to record for the last, let's say 100 instructions, how many times one cache line the data has been requested. Okay, so I think most Intel CPUs implement the least recently used algorithm because they are much bigger CPUs, bigger die, also much more expensive. But for mobile devices, like ARM embedded devices, they just use a random approach. So, which means the circuit level, you don't need to remember anything. Every time you need to bring some data, new data into the cache, the cache is full, you need to evict something, you just randomly evict one, unless there is something already available. We actually proved that. In the document, they didn't say it. We actually, in one of our projects, proved that that random replacement policy only kicks in when there is no available. If there is one available one, it will always go to the available one. That makes sense anyway. So that's what the replacement policy is. There are actually some other concepts associated with cache. For example, there are inclusive cache, exclusive cache, or not inclusive cache. Inclusiveness means if the data is in L1 cache, it is also in L2 cache and L3 cache. That's called inclusive. So all the upper layer, higher layer caches always has the lower layer cache data. Then there are also exclusive ones. If the data is in L1 cache, then it will not be in L2 cache. So most CPUs right now, they are neither inclusive nor exclusive, which means for different data, different things could happen. For some data, maybe all three layers of cache has it. For some data, only L2 cache data has it. But I think most Intel CPUs are inclusive. And those information usually is very difficult to find. You cannot find those information in any document. Even if you want to find, for example, when we do a LS CPU here, the only thing we get is cache size. We don't get how many ways, how many sets this CPU, this cache has. We didn't get this information from this output, right? You need to, actually, I think you can get that. The CPU actually, maybe there are some system registers to tell you those information, just the LS CPU is not reading that information. Before we move forward, oh yeah, we can move forward. Okay, so now we have a basic understanding what CPU cache is. Do you have any more questions here right now? Everyone's good? Okay. So then what is cache side channel attack? So basically, side cache channel attack is, first of all, it's a side channel attack. It's not like you can directly read data from the cache. There is no interface for you to do that. It just utilizes the time differences between a cache hit and a cache miss to infer whether some specific data, including code, has recently been brought into the cache. If the data was brought into the cache, then obviously there will be a cache hit. Then if you access that data again, it will be very fast. If the data is not brought into the cache by anyone else, then you want to access the data, you have to retrieve from the memory. Then it will be quite slow. And using that timing information, you can know if the other party, anyone else, has been accessing data. And just use that information, you can do a lot of things. Just use that information whether someone has accessing some specific data, you can do a lot of things. You can steal crypto keys, you can infer crypto keys, you can attack another computer, you can build a covert channel, and Meltdown Spectrum uses this approach to build a covert channel to send things out from a more privileged domain. Okay. So here is another example. This example is more like an ARM-based example actually, but the idea applies to Intel architecture as well. Let's say we have one instruction. This instruction load R1, R0 here, which means we are using R0 as an address. We're moving the data at the memory location R0 to the register R1. Okay, so this can corresponds to move EAX some memory location instruction at Intel architecture. So like I said, for most software developers or system developers, what you imagine is IR0 is 3000 in hex. It points to the memory location 3000 in hex. The data there is just one. Then after this instruction, what happens is you move that value 1 to register R1. That's what the system developer, software developer believe. And this is actually true, right? Uh, the result is actually correct. The only difference is what happens under the hood may be different. And what happens under the hood is when this instruction runs, the CPU will first check if that address 3000 hex, the data is already in the cache. If it is already in the cache, it will just directly request data from the cache, move to R1 register. If it's not in cache, then that data will be brought into the cache first, then move to the register. Okay. So the first part, and the first and the second, the cache miss and cache hit, the difference is if you are going to actually moving data from memory to the cache. And that makes a big difference in most cases. So for attackers, what you can do is, if you can measure the time right before execute this instruction, and measure time right after you execute an instruction, then you can infer whether the data at R0 is already in the cache. That's what you can do. That is what happens at the lowest level. Is just this kind of proof of concept code, just like this. At the lowest level, it's just like this. Nothing fancier than this. There's no fancy instructions to directly read from the cache. No such thing. Yeah. So based on this very simple, we can call it a very simple building block. Based on this very simple building block, in the last 15 or let's see, probably 18 years, I think the first cache side channel attack came out maybe 2002 or something. That's the effect time and the prime and probe approach, probably that time. So in the last 18 years, there has been many different approaches based on that very simple observation. Okay, they all have very fancy names. I even contributed one myself. I have a paper called we call it prime and count. That's also a new approach we published 2 years ago to attack trust zone. So all those approaches right now, they have a very kind of catchy names like this. It's always like evict plus time or evict and time, those names. But those names doesn't really mean the attack can be carried out in simple 2 steps. They are just very catchy names. Okay, we will look at most of them. Evict time, prime and probe has been very popular. Flash reload is more popular than flash. Flash is also very useful. Then for some CPUs, there is no flash instruction. Then we have evict reload. We're going to look at those at code level. So if you're interested in this work, there is actually a very good master thesis I advise you to read. This guy, Maurice Leap, from, I don't really know where this university is. It's in Europe, I know, but I don't know which country it is. But he has a master thesis called Cache Attacks on ARM. This is a very well-written master thesis. He is part of the team that discovered a lot of cache side channel attacks also part of the team that discovered Spectrum and Meltdown. And they are keeping discovering new things every day. Even several days ago, they published a new paper on some kind of new cache channel. I don't remember what it is. So they have done things from ARM Cortex-A to Intel to SGX to everything. But I haven't seen them doing things on Cortex-M yet. So that's why actually I want my team to work on Cortex-M CPUs to see what kind of cache attacks are possible there. Okay. So this is a very well written master thesis. If you search this, you shall find it. The second section, the background part, he has a very good writing about the history of cache channel attacks. And so the first one is probably published 2005, so it's 15 years ago. Okay, so 15 years ago, PMO, they published this paper in a crypto conference. So when the first time they published, I don't think it's in security conference, it's in crypto conference. They're trying to steal AES keys, that's what they're doing. So they developed two approaches. One is called evict and time. The other one is called prime and probe. So the basic idea of evict time is very simple. The first step, you measure the execution time of a victim program. We assume there are two programs. One is the attacker's program, another one is the victim's program, and they run on the same box. This depends on where you run this, right? If you're talking about cloud environment, you're talking about attacking the level 3 cache, they don't have to run on the same, virtual box. They are running on the same physical box, but they are not running on the same virtual box. And as a virtual box, there's basically no way to find out if they are running on the same. It's hard to find out if they're running on the same physical box, actually. So those two applications, two programs, the attacker will first measure the execution time of a victim program, let it run, and to say how long does it take for attacker to access some data to measure time. Then it try to evict a specific cache set. Okay. We always talk about what is cache set. We talk about what is evict. So how to do that? How do we evict a specific cache set? Remember, there's no special instructions for us to use. The instructions we're talking about here is exactly the same as the move instructions we have, right? So how do we evict a specific cache set? Let's go back to this example. So what we are interested in is whether the victim has been putting data into this cache set. Why we are interested in that doesn't matter right now. I just tell you at a very high level, from the AES execution, eventually we can map something there. Okay, we're interested in if the victim has been putting data into this cache set. Okay, so how can we know that? The first, what we can do is we first put this set. There are 4 lines of it. We put this set, all 4 lines. We put it into some known state, some state we know, right? So we just keep reading memories. We just keep reading congruent memory addresses, memory locations, which their data will be put here. We keep doing that. We don't know how many times we have to do it to make them fulfill this one. Why? Because it could be random. It could be for ARM architecture, this could be random. So let's say we have 2 congruent memory address. If we read them one after another, what will happen? We could bring both of them into this cache set. Or we may only have the second one into the cache set because the first one was replaced by the first one, right? That makes sense. So but if we have 4 addresses or even more, maybe 5, 4 would be enough. If we have 4 congruent addresses, we keep reading, and eventually, at some point, all 4 addresses will be, 4 probably is not good, maybe a little bit more. Yeah. Let's say we have 8 congruent addresses. We keep reading, then eventually we know that those 4 of those 8 addresses will fill the whole cache set here. Okay. Then we can measure if they are in the cache set by reading those addresses. If they return very fast, we know they are in, all of them are in the cache set, in this cache set. Then we run that victim's program. And that victim's program may bring some data into the cache. When that happens, it will replace our data. Then we access our data again. You can say it will be very slow. So that is actually the prime and probe approach. So the evict time approach is actually a little bit simpler. The evict time is not very effective. It's to measure the execution time of a victim program, then evict a specific cache set, then measure the execution time of the victim program again. If the victim program does not use anything in the cache set, then the execution time should be the same, right? If the victim program does use some data in the cache set, because we evicted, what will happen? The victim program, the second time we measure it, it should be a little bit slower. Okay. So that's the evict and time approach. So what I just described to you is more like the prime and probe approach. So the first step is called prime. Prime is basically means get ready, right? So the attacker tries to get the cache ready. So the attacker will try to access many congruent addresses. The goal is to fill a full cache set. And this step, because the eviction in some architecture like ARM is random, so this step is also a little bit random. There is no deterministic approach for you to say how many times you need to access to fully fill this. You don't know. But then the second step, the victim runs. The victim may access some of the data which will go to this cache set. Sorry. Then the third step, the attacker will just try to access all those congruent addresses again. If some of them is slow, which means the attacker has evicted. The victim has evicted. So if the victim evicted, then we know the victim has been accessing some congruent address. That's basically what we are trying to find out. Those addresses may be sensitive data address, maybe sensitive instructions address. Depends on if this is which level of cache and also if this is instruction cache or data cache. So the problem with this approach is you are working on a cache set. The benefit of this approach is no special instruction is needed. There are not many. So I said that there are not many instructions that you can directly interact with the cache. There's no instruction for you to read the cache. But some architecture like Intel, there are instructions for you to clear the cache. ARM, there is no instruction for you at the user land to do that. The kernel has a cache instruction to do that, a privileged instruction. But Intel, there is a instruction called CLF flush, basically. Maybe it means cache flush, but why is CL? C probably is cache. What is L? I'm not sure. Anyways, CL flush. I will show you later the instruction. So that instruction is available for applications. It's not privileged. So which means any application can flush a specific cache line, okay? So that's why we have another approach called a flush and reload. That instruction will take a virtual address as input and flush the cache that stores the data from that location, flush the cache line, only flush the cache line. Even if by having that virtual address, you don't really know which cache line that data is. You don't, right? Because it could go to different ways. You only know which cache set it will go to. You don't know which cache way it go to. But that instruction will guarantee it will flush out the cache line. It doesn't tell you which cache line it is, but it will flush out that. Okay. So in this kind of attack, what the attacker and what the attacker can do is the attacker and the victim, they will share some libraries. Could be dynamic libraries. This is very common, right? For example, if you develop a program on the computer and your program want to use AES, and you probably can use the OpenSSL AES library. And on that virtual or physical box computer, there is another web server also use the same OpenSSL library. Then you guys share the dynamic library. Then the attacker will try to, for example, there is one address that is an address of instruction of that library. The attacker will try to flush that memory out of the cache, use that specific instruction, CL flush instruction to flush it out. When you flush it out, you know that that address is not in the memory, okay? Then the victim may or may not access that block again. If that victim accesses that block, what will happen? That block will be brought back into the cache. Not necessarily at the same way, but definitely in the same set, right? So you can imagine that block you want to check if that victim block brings in could be after a predicate, right? Maybe there at the C level there is a if. Could be if the crypto key is 1, then we will do this instruction. If the crypto key is not 1, we will do the next instruction. Then we put the address of that instruction, we flush that out. Then later we measure if that instruction, the location was brought back to the cache, then we know the key is 1 or 0, right? I'm talking about a binary condition. It's not in real way, it's much more complicated than that. But you probably get the idea, right? So you can imagine the third step is very simple. The third step, the attacker will try to access that block himself again, and just measure how long does it take to access that. It could be an instruction of move. It could be an instruction for others, just to measure how long it takes to execute that. And use that, you can just infer. The attacker just can infer what's going on there. So that's the basic idea of flash reload and prime and probe. So today we will do some simple examples. Next week we will show a little bit more advanced examples. And after that, next week I'm trying to also ask you guys to do Meltdown and Spectrum, but I'm not sure right now if my computer can do that, because I show you guys. Because my computer is a new computer. My old computer, I can do that. But you can see, this is my new computer. My new computer can actually says Meltdown is not affected. Okay, if I do LS CPU, it says Meltdown will not affect my CPU. If about a Spectrum, it says it's already mitigated. Okay, So I'm not sure if there is any BIOS setting or something I can disable this mitigation, but this is the only computer I have right now. But if right now you can actually do a LS CPU on your own computer, even if it's a virtual machine, you can do that. You can say if your computer already patched, your CPU already patched Meltdown or Spectral. So this is actually some firmware patch. It's not like a physical fix. So if they are not patched, you should be able to run it on your computer. Right now, I'm not sure if I can run it on my computer because I have a lot of virtual machine try to do the test, and the virtual machine probably disabled what kind of a patch they have. I don't know. Yeah, so I will try to figure that out next week. Okay, so today we are going to see several examples. Oh, by the way, cache side channel attack should be doable on all the CPUs, no matter it's Intel, ARM, or AMD. But the Meltdown and the Spectrum probably won't work on AMD CPUs. AMD CPU doesn't have this problem. Is any of you using AMD CPUs?
I am.
You are using an AMD CPU? Oh, so it may not work on your CPU, yeah. Okay. So
now, would my virtual machine also inherit that?
your virtual what?
So if I'm running a virtual machine on the CPU in question, would it inherit that defense, or is it?
Well, if it's an AMD CPU, the CPU doesn't have that vulnerability in the first place. So the virtual machine will not have that problem at all. Yeah.
Makes sense. I do have another Intel machine that I can use.
Yes. Because this one came out like 2 years ago, there has been patches for all the newer CPUs. Yeah. So what we're going to do with this one is we're going to use the SateLab. But like I said, we're not using all his code. I will upload the code later. So let's see what I have here. So I have the cache time code. This cache time code right now I'm using his code. Cache time. I was trying to build new ones here. Okay. So this is the code for us to measure. This is a code for us to measure the access time for some memory locations. To do this, you need to include those two header files. I will just copy this to you. In the homework, I will just give everything to you. So you can see here, we have a global variable. So this will go to the data section. This is a global variable. The global variable is big here. Okay, intentionally we build it big. So 4096 bytes is one page. Physically, it's one page at the for Intel architecture. For ARM, I think it's the same thing. One page is this, and this array is actually 10 pages. So each cache line is only 64 bytes. Right? We have a main function. We have a global variable. The value of it doesn't really matter. Then we have two. Oh, sorry, this is a local variable. This is a stack local variable. It doesn't have to be here. It can be registered as well. Then here we have another two local variables, but instead of putting them on stack, we put them on registers. So we do not want much noise there. That's the only reason we do that. Then there is another pointer. We make it volatile because we could change it. Okay, so this is a pointer. There is another, just a counter, a local variable. Then the first thing we do is we initialize this array. So the purpose of this initialization is not really initialize the value of it. The value of this array doesn't really matter to us. And also we're only initialize 1 byte. The real reason for this is when we run this program, what happens? The operating system, we type this cache time into the shell, we run it. The shell will fork itself. After it forks itself, it will execute the system call eve cve to replace itself with this new program. Then this new program run. Okay, I mentioned to you at some point, Linux is trying to make things, the OS is trying to make things as fast as possible, right? Uh, because of that, some of the memory, because it forks itself, so it will have the old memory, uh, memory, old memories. So as long as, so if you want to clean up those memory, if you want to change those memories, they all take time. So the Linux will, the kernel will not do that until it has to. So it's called the lazy load or whatever. I think it's called lazy load. Yeah. Um, if you Google copy on write, you will find out. Uh, Basically, it's copy on write, COW, call. Okay, which means uh, only if when we write things to this array, it will actually create this page for this process and put data there. So this step we're trying to do is we guarantee this 10 web, this 10 memory pages are created, and the value we put there doesn't really matter. 110 doesn't matter, and we don't have to put 4 KB data there. We just put 1 there. That will guarantee each page is allocated. Then we will use this flash instruction. I will show you later. This one maps to the CL flash instruction. And you can see this instruction takes the address of a byte. So we are using the beginning of each page. So this is an array. We get the address of it. We're giving this address to the flash, and this flash instruction makes sure that, for example, here we're putting 1 there, and this flash instruction makes sure that that 1 is flushed out of the cache. It will not be in the cache anymore after this loop. So flush all of them out. Then we try to access some array items again here. We're accessing the first 9 of the page number 3 and page number 7. We're writing things to it. Reading should be the same, actually. So what this happens is the value of this address will be brought into the cache again. So here we make sure all of them are flashed out of the cache. Now after this, what happened is 3 and 7 will be brought into the cache again. Okay, of course, like I said, there could be some randomness. There could be something we don't know, because this is the level we can operate. What actually happens inside of the CPU, we don't really know exactly step by step. Okay, so all we know is from what Intel has been telling us from their document, from all our experiments. So what exactly happens, could be some commercial confidential secrets here. We don't really know. Okay, so 3 and 7 probably in this case will be brought back into the cache again. Then we want to access all of those 10 bytes again and measure the time. Okay, the first thing is we get the address of those things. The reason we do that is we want to reduce the noise, because even this will take some time. So so this is the line of code. We actually read the data from the memory location, and we only want to put this statement inside of the measurement. Okay, so all other calculation we put outside. Okay. So the measurement, we're using a CPU feature. There is a Intel CPU feature to do that. A different architecture, they probably provide different instructions for you to do that. Sometimes it's part of the debugger, sometimes it's part of other modules, like measurement performance modules. And this is a save function that eventually maps to those instructions. And you can see here we're going to get the current time, and we put the current time in time 1. This one we're putting the current time to time 2. Then we use time 2 to minus time 1 to get how many CPU cycles we have been executing this line of statement. The argument here doesn't really matter. Besides giving out the time, it will also give out another signature we are not going to use, so it doesn't really matter. Okay. Then we just print out how much time this has been used. Okay. So if we run this program, I think I named it CT1. So if we run this program CT1, you can see the time. The first one will take 800 CPU cycles. The second one 400 CPU cycles. The third one one. So this one is the second one actually. Yeah, the index starts from 0. So this one is 189, and the third one is 173, right? And the seventh one is 186. Okay. So you look at this, you do not really feel 3 and 7 are faster, right? Not really. Some others are even faster. That's because of the randomness. But if you run this multiple times, for this one, say this time I run it, it's very clear. For 3, it's only 41 CPU cycles. For 7, it's only 39, but all others are quite big numbers, right? So there is some kind of randomness. Oh, this one the same, right? The same. So right now, so this time is not consistent. So you can say it's not that consistent every time, but if you run this 1,000 times and get an average, you probably can get a pretty good idea that what is in the cache, what is not, right? Does that make sense? And also the first one takes longer time. There could be reasons for that as well. I'm not sure why in this case. So it's quite consistent for now. 3 and 7 is quite faster than that. Let's change the code a little bit. Okay, let's change the code a little bit. For example, let's just try this to 2 and 8 first. 2 and 8. Then we compile it again. Run this one again. Say 2 and 8. They are slower. Okay. So why do we? Another thing you notice that is in the source code, the data we are reading are actually far away from each other. They are very far away from each other. We didn't really calculate the number of sets for the CPU. We will do it later. We didn't calculate how long is that set part, how long is the tag part, but we know they are quite far away from each other because each cache line is only 64 bytes. They are so even those two, when we're accessing them, they are like at least what 4 kilobytes away from each other, which means even if we bring one to the cache, the others should not be affected. There are other cases. For example, you bring one cache line into the cache, the lines, the blocks next to it, nearby, could be brought into cache as well. The CPU will decide, because the CPU may believe that because you access this memory location, it's very likely you are going to access the next 64 bytes. So they will bring that into cache in advance to make things faster. So it's like the CPU is It's taking a chance there to make things faster. If it doesn't happen, it doesn't really lose much. But if it happens, if you're actually accessing it, then it saves a lot of time later. So what we can do here is, for example, every time we flush it, okay, we can do another experiment. What if we do not flush this? If we do not flush this, what will happen? It will get very fast, right? Everything should be fast. Let's try if that will be the case. See, everything is fast because no, it's sometimes it's fast, right? So for example, this one, it has nothing to do with that 2.8 we preloaded. Everything is fast. That's because we didn't flush it. Everything is in cache. It's quite fast. Right? So what else can we try? What else do you guys want to try? Here. What if we do not write this? We just read it. How can we just read it? We do a print, maybe. Yeah. So for example, if I do a plus plus, it will also write it. So let's just do a print. This. Print f percentage d. We don't really care about the value of it. Just want to say this. Oh, did I miss something? Okay, good. So the flush is back. Okay. Let's try to run this again to see if it works. Okay. So this time you can say 8 is much faster, but all other times, so yeah, this one is 8 is much faster, but we don't really say 2, right? We don't really feel 2 is, oh, this one 2 is looks like a little bit quicker. Ooh, so 8 is really fast. So there are some randomness somehow, sometimes we cannot explain, but you get the idea. So maybe write is a better approach than just read to make sure it's in the cache. Yeah. So those kind of things you can only just text. There's no document for you to know which one will guarantee better performance as an attacker. Okay. Any questions so far? We're good. Okay. Now let's get back to the slide. I want to show you guys the CPU. I forgot to put the links. Yeah, I think I forgot to put the links here. Let's search the CPU and do a little bit of calculation. The CPU is this one. This is the CPU we have. Connect the browser here. If we search the CPU, there is a website I found. Okay, so this, I think it's this website. Not really. There is a website I find. CPU work. Not this one. Okay, this website actually tells me So all other websites, even the Intel website, doesn't tell me how many cache weights are there, uh, how many separate caches are there. Okay. So you can say here, this is the CPU I'm using. This website tells me, so L1 cache is 32 kilobytes. There are 4 of those, and each of them is a 4-way set associated cache. That's for the instruction cache. So can go back here. Yeah, 4 of those, which means if I have 2 cores, I have 32. So that's why here I have 4 cores. I have 2 cores. 2 cores should be 32. So it matches 32. Okay. Then since each of this is 32K, I need to drag this one somewhere. Oh, there are some chats. Any questions here? Oh, someone saying wiki has this. Okay, whatever. Let me see if I can drag this. If we do some calculation, 32K, we have 32K. So 32 times this. This is 32K. Then divided by number of ways, which is 8-way. It says it's 8-way. The instruction cache is 8-way. Then each of them is 64 bytes. So which means we have 64 sets. So in this CPU, which means in this CPU, the offset is 6 bits. The this part is also 6 bits. So all other things are 10s. There are only 64 sets here. If we talk about the L2, let's say L3 cache, we have 8 megabytes. That's 8 megabytes divided by number of ways, which is 16 ways. That's a lot of sets. Ooh, that sounds big. That's 8,000 sets. Let me see. Yeah, I think so. That should be correct. So that of the 8. So the level 3 cache had 8,000 sets, and that will take how many bits? 10 bits is so that will take 12 bits to identify the sets. 2 or 30, maybe 13 bits, for that. Okay, so that's for to measure the cache. Then let's do a object dump of this to check the instructions. So this function doesn't have, this program doesn't have much code, only the, by the way, this 32-bit is only the main function. As you can see, let's see what is interesting here. This is a flash instruction I talked about, and this instruction takes a virtual address as input and flash it out from the cache. So that's maybe the only instruction we have that can influence cache here. All other instructions are just the regular instructions. They are just moving things from register to memory. Okay, this one will directly influence cache, but the argument is also still just memory. Okay, then for the time measurement, you can see that this is the instruction we are using. We are measuring everything between this. So look at this. What idea do you have? when I look at this, I have a lot of idea. I mean, this can be even optimized. Even this can be optimized. The code we have here, the code I'm using is from system. The code we have here is at C level. At a C level, we're doing this, right? This is what we're doing. So we're measuring this. But if you look at this assembly code, you realize there are probably things you don't want to measure. Maybe they will not affect the results that much, but because you are measuring everything here, so everything in between maps that instruction. Okay, that's a statement at C level. That's a lot of instructions. Some of them probably will add some noise. You probably just want to measure one instruction, which is a specific instruction that you try to read from that specific address to register. So if we can refactor this, rewrite this in assembly language, probably we can get better results. A lot of noise we see, probably some is because of this, I think. Yeah. Does that make sense? Yeah. So if you want to do a more accurate measurement, you can embed some assembly here, remove some of the, of course, some of this could be very fast, but some of this could be slow. And you are doing that multiple times. This is also slow, right? That will affect our results. Because there are multiple memory read, memory write, it's hard to explain which part is that. Interesting. Okay. Yeah, if some of you are interested in this, you can work on this and show us the results next week to say if you just rewrite this at a assembly level, do you get more consistent results instead of the randomness we see so far? Okay. So next we are going to see the flash reload. The flash reload, we are going to use their code as well. So their example is not a very good example. So next week, I'm trying to develop a better example for you guys. The problem they have is the example they are showing, they didn't use two processes. So everything is in one process. I will just change it a little bit to make it's a two different process and they share a library. But let's take a look. This is one program, one C program. There is a huge array here, 256 kilobytes of array. Okay, each bigger than that actually. This because one page is 4K, so this is actually 1000K, right? This one is 4K. This is 1K. So this is a megabyte. This is 1 megabyte of global variable. Okay. Fortunately, our memory is big enough to handle that. So this is an array. I don't think we have to do this big actually, as long as the addresses they are. Someone can test this as well. As long as those addresses are far away from each other, they do not influence each other, it should be okay. We don't have to make sure they belong to different pages. Okay. Then there is another global variable temp. Then there is a secret 94. That's our secret. Remember, we are trying to infer that secret. Then we have a threshold set, cache hit threshold. So basically, this is the number of CPU cycles. We read that we read some data. If the time we spend, the CPU cycles is smaller than 80, we say this is a cache hit. Otherwise, we say it's a cache miss. Okay. Then let's say the main program. The main function calls those three functions. The first one is a flash side channel. The second one is the victim program. In this case, it's just a victim function. Then it's a reload function. So this is exactly the flash reload approach. We flash, we run the victim, then we reload. And let's say how flash works. Flash, very simple. We first do to avoid copy on write. We initialize those 256 pages. The data here is just to make sure we're doing at the somewhere middle in the page, not at the beginning or end of page, because beginning of the end of page, there may be strange things happening. Maybe there are some system level optimization to bring things there, right? Then we make sure we flush them out. So using the same flush instruction. Then we run the victim program. The victim program will just read one thing. It will just read one byte. Okay, that byte is determined by the secret number here. The secret number here is 94. Okay, so it will just read 64 times that page size plus the data time. Okay, so all that 256 bytes of I should not say bytes, 256 blocks or lines have been removed from the cache, flushed out of the cache. And one of them, the secret, indexed by the secret, will be brought back. That will be brought back to the cache. Then at the third step, the attacker, the same thing, we try to access all those 256 blocks again and measure the time. This is exactly the same code. Okay, we measure the time. Then if the measure the time is smaller than the threshold, then we say that is the secret we are trying to set. Okay, this is a secret we reveal. Okay, so you can say this code actually shows that we can build a covert channel with this. So covert channel means a communication channel that is not known to everyone, but two parties can use this to communicate. So in this case, the victim and the attacker are not necessarily victim or attacker. They could just be the sender or recipient. So the victim here could be the sender. The attacker here is actually the recipient. The sender is trying to send out a message. So imagine those are two running processes. The sender is trying to send out a message 94 to the recipient, and the recipient use this way to recover what the message he is sending. And because there are 256 chances, so actually we are sending out 8 bits of message, right? We're sending 8 bits of message. If we can even improve this. If we add another thing here, then we can send out another 8 bit of message. However, you need to think about, this is something the attacker and the sender and the recipient will negotiate before how many things they are sending out. Okay. Does this code make sense to everyone? Any question here? No one has a question? Just want to see the demo? Okay, let's say then we run this flash reload. See, it print out the secret. We run this many times. It's quite consistent. Oh, this time it didn't get lower than the threshold, so we did not get any secret. But most of this is very, a lot of time we missed. Most of this is quite consistent. See? Yeah. Let's try to change the code a little bit. We'll try this. Flash reload. Let's say, what if we want to send out 2 messages? Yeah, let's send out 2 messages here. Usually I don't use VI, so let's say another message we want to send out, what do we use? Now we just use a fixed message, a fixed one, 20. This one with 20, secret is just 165, right? So now we're supposed to have two messages, two secrets sent out. Let's see if it works. No? Why segment fault? That makes sense. Why segment fault? Do you guys see any problems? Why there is a segment fault?
Did our secret go too high for what was available for the resources?
I don't think so. It's 256, right? It's 256 here. I didn't change anything here. Let's see. This address is going from here. Why is segment? Okay, any say experts say the problem? 20. Okay, let's comment this out. Oops. Let's comment this out first. That makes sense. So now we changed the secret number. Okay, what's the problem? This is too big. This is not supposed to be too big. It was like 94. One?
94 was the previous one.
Yeah, 94 was the previous one, right? This is correct. I mean, if I use something bigger than 256, I mean, that could be a problem, but why this is a problem? That's why weird. That's very weird. Okay, it probably changed to something I didn't realize, I guess. Okay, this one no segment for, but this one you can see it works. Right? Sometimes you cannot identify the secrets, but most of the times you can. We didn't initialize it? We did. So that's weird. So this should not be a problem. This is big. Oh, how big is the data? Oh, the data is in the middle of the page, so should not be a problem. Okay, interesting. Something we can look into. It's always segment fault. So we are not able to have a memory that big. Looks like that way. But at the state level, doesn't that make sense? This one we're trying to assign it, right? This one doesn't get any segment fault because here the I is already bigger than the secret. So why did it get a segment fault? Okay, anyone has any idea what's going on here? Shi, Toma, do you say why you couldn't have a segment for here? That's a bit weird. This is a value. This is one solid. This is in the middle. Any other idea? Phil?
I was only spitballing from what it looked like at face value. I mean, I wonder if the bound's exactly 127, and if we go to 128, it pops over, but it's still not still not a good explanation. It's just a guess.
Yeah, that's a bit weird. I'm not sure what's going on. 127. Okay, 127, no second and fourth. Let's try 128. Yeah, you're somehow right, but why? I don't know why.
Yeah, that's the worst part about that is it doesn't really matter that I'm right or not.
Let's see. Why is that? Is that because of there? There, huh? This one's so big. This is in the middle of it. It's not supposed to have a second fourth. This data doesn't really matter. It's a small number. Especially we already used it here. So, okay, so the second and fourth, well, the second and fourth may not even be here, maybe. The second and fourth may be somewhere here. Yeah.
So when we generate this array, we're gonna set it to secret times 4K.
Yes.
And but when we're accessing it to initialize it, we're going to add the delta in every time, which is eventually going to break past those array bounds, correct?
No, because the delta is not that big. The delta is only 1K. Right. Okay.
But even if we went over by a byte, we'd still go out of bounds on the array, correct?
But let's say, for example, if that happens, which specific line you think may have the problem? Still this line, or?
I got to think about that for more. I would almost think the initializer would have made the. I mean, we could run it in GDB and know.
Yeah, I'm also thinking about that, but it doesn't make sense because the initial is not using the secret.
You're right.
Right. Yeah. Okay. Yeah. Let's just debug a little bit to see what's going on here. How do I should compare this one again? Let's do GCC. Let's do G. So G will give us all the symbols we need. Then we do flush. No, it doesn't give us a.alt. We do a.alt. Second foot. Good. Let's just do. Oh, there's a virtual machine that installed a data there, which is good. Then let's just run this. Okay, let's just step out to see which function triggered the fault. Okay, not the initialization. Yep, that's yeah, this line triggered the problem. But why would this line trigger the problem? That's fine. Okay, it is this line, but why?
I feel like you might have explained it when I pointed at the initialization and you said no, that doesn't involve the secret, and that's why it wouldn't blow over. But yes. Sure enough, line 27 is the one that involves the secret, and then that delta offset presumably is going to knock it past the bounds of the array.
Really? Not really, because the secret could be as big as 256, right?
Right. Nope. Yeah, I got to throw that out too. Yep.
Yeah. So that's huge. So
yeah, you couldn't add your way past that.
Exactly. Yeah. Okay. I need to debug a little bit to figure out what's going on here. It's a bit weird. It's really weird, huh? But somehow you're right. I mean, 127 will not trigger a problem. Huh. That's also weird. Why? Okay. Anyway. Okay. So next week I'm going to change this code, show you guys how can we do this with two process, because that will be a much more useful scenario. This scenario right now we have doesn't. Oh, also you can try this on your virtual machine. You may not, and let me know if you have this problem. This may be related to a lot of things, I think. After we learn about this, so next week you can also build some covert channel for programs to talk with each other. So one of the projects I did before is to build a covert channel between the ARM trust zone secure word and the normal word. So all your phones, tablets, they have this feature called trust zone. So you can execute some trusted applications in the secure word and run Linux in the normal word. And when you talk with each other, they are only supposed to talk with each other using some predefined channels. Some special instructions need to initiate that. But because they share the CPU, you can imagine two applications running in two separated, isolated environments. They can conclude to communicate with each other using the technique we just saw, something like that. Very complicated, much more complicated, but the basic idea is like that. Okay, so that's it for today. Any questions? Is this a big change from what we discussed so far this semester, or you think do you feel it's a big change, or you feel somehow they are related?
Yeah, it's quite different from what we have discussed so far.
Yeah.
I think it's more interesting, personally.
Yeah, I was about to say that. This is more interesting.
Well, okay. When you say meltdown spectral, you will say that, so it's really interesting. But I personally still believe the software part is very interesting. Okay, cool. I'll see you guys next week. I will try to see what's going on here. See you guys next week.
Thanks, Dr. Joe.
Yeah.
Thank you, Professor.
Okay, thank you, everyone.
Actually, yeah,
Yeah,
I suppose I'm asking it a bit too late. Are you
It's okay.
gonna? I suppose, are you going to release the homework for this week? When are you planning to release it? I mean, that's the question.
Probably several days from now. Don't worry about it. I will not make both homework deadlines on the same day. I will give you enough time. Yeah.
Thank you.
Is that what you really want to ask?
No. Well, well, technically yes. Okay, yeah, technically yes.
Okay, cool.
Okay, have a good one.
You too. Okay. Bye, everyone.